discussing how the peculiar velocity is related to the density fluctuations in the linear theory of density perturbation. And we had worked out this relation between the peculiar velocity and the density contrast. This relation between these two involves this function f, which we had introduced in the last class. F is the logarithmic derivative of the growing mode of density perturbations with respect to the scale factor. Now, if and it also has this relation also has the scale factor and the Hubble parameter in it at the epoch when this relation is being applied. Now, let us first look at this function f. F is defined as d ln the growing mode d ln a. Now, we have seen that in the Einstein de Sitter model, where omega matter is 1, the growing mode is proportional to the scale factor. So, we can write it as some constant into the scale factor a. In this case, f is equal to 1, because when you take logarithmic derivative, take the log of this and differentiate with log of a, you will get 1. Now, if you we can easily calculate this for any arbitrary cosmological model using the expression, general expression we had derived in the last class. In the last class we had derived a general expression for the growing mode in terms of the scale factor and the different omegas, omega matter, omega lambda, omega curvature. So, one can derive that. It turns out that to a great approximation, f can be written as a function of the matter density alone, and to a great degree this is of accuracy, this is omega matter 0.6. This is found empirically, in the sense that you take cosmological model with different values of omega matter, evaluate the growing mode by evaluating the integral relating d and a, and then differentiate with evaluate the logarithmic derivative, and you find that this is to a great approximation omega matter to the power 0.6. So, we can write this as f of as a function of omega matter alone. This is found as an empirical relation, and this is approximately equal to f omega matter approximately equal to this, okay, to a great degree of accuracy. Okay, it's not, you cannot show this, cannot derive this, but it is found empirically by fitting it, that you can represent it as omega matter to the power 0.6. So, the relation between the peculiar velocity and the density fluctuations involves this f, which depends on the omega matter. In addition to that, it has the scale factor and the Hubble parameter. It also has this factor of 4 pi, and you have this integral. Now, let us look at this integral. So, let us consider the simplest possible situation where I have an overdense region. So, if I have an overdense region, let us ask the question, what is the peculiar velocity produced by this overdense region with this integral? Now, this integral is exactly the same as the integral that you get when you calculate the gravitational attraction produced by an overdense region like this. That it is exactly the same, 1 by r square, and this is the mass there, right, exactly the same. This is the density, this will be the density there, exactly the same. The factors outside will be slightly different. So, we know from that when I integrate this, let us look at the direction. So, this is the point where I wish to calculate the peculiar velocity. This is the point x, and I have to integrate this expression weighted with. So, there is a uniform over density over here, uniform excess density inside this spherical region. So, I have to do this integral, and we know that when I do this integral, this is the gravitational attraction acceleration on a point over here. So, we know that this is going to be proportional to, it's going to be directed opposite to x, it is going to be in the direction opposite to x. That is clear from here because you have a minus x over here, right. So, it is going to be directed opposite and it is going to fall as 1 by x square. Okay. So, from this we know, what we can tell is that if I have an overdensity, a spherical overdensity like this, it will produce a peculiar velocity which is going to be pointed towards it, and it will fall off as 1 by r square as I go further and further away. It is just like the gravitational attraction produced by a point mass, just that the numerical coefficients multiplying it are going to be different because the factor over here is different, and the numerical coefficient which comes over here, if you know the density perturbed fluctuation, then the numerical coefficient that comes over here involves the value of omega matter, right. So, in principle the an overdense region produces a peculiar velocity pattern that looks like this, and the overdensity grows because of the flow of material towards it. Similarly, an underdense region, if I had an underdense region delta less than 0, it will produce a repulsive, it will have matter flowing out from it. This is the growing mode of density perturbations, and the matter flowing out with the peculiar velocity will fall off again as 1 by x square. Okay, so, an overdense region produces a peculiar velocity pattern towards it which falls off as 1 by x square. An underdense region produces a peculiar velocity pattern that flows out and that falls off as 1 by x square. Now, this provides you a very interesting possibility. Let me briefly mention this and then move on to something else. So, today is let me move on to something else. Let me first tell you the possibility. There are galaxy surveys, for example, where they can actually measure the positions of galaxies, where they can measure the distribution of galaxies in space. Okay. Now, if you can measure, if you can determine the distances directly, we have discussed how distances can be directly measured. For example, the Faber-Jackson relation, or through the Tully-Fisher relation. So, if you can measure, if it is a spiral galaxy, if you can measure the rotational velocity, then you can infer the luminosity. Once you know the luminosity, you can predict the distance because you can measure the flux. So, if you can measure the distance directly, then you know d, the distance. You also can measure the redshift z. So, from these two you can measure, you can determine the peculiar velocity, the radial component of the peculiar velocity. The radial component can be determined. Now, from the galaxy counts, you can also count the number of galaxies in a region. So, from a galaxy count, what you can do is you can determine the number density of galaxy as a function of position. Now, what you can do is you can subtract the mean number density divided by the mean number density, and this will give you the density contrast for galaxies. Okay, you can do this observationally. So, you can, if you can find out the distribution of galaxies in a region of space, determine their distances or determine the distance of some of them, you can determine the peculiar velocities. From there you have the radial component of the peculiar velocity, you have the delta. So, you can now use it here, you know the left hand side, you know the right hand side. Okay, then you can use it. So, you can use it to actually determine these constants over here. You know this, you know this. So, the unknown thing is the constant over here. The constant over here, if you do this at present, then the scale factor is known, h naught is known. The only unknown is this function of omega matter. Okay. But there is a small caveat. What you can measure is the fluctuation, the density contrast for the galaxy distribution. What the density fluctuation that comes in over here is the dark matter. The dark matter is a dominant dynamical mass component in the universe. You cannot measure this, you can't see the dark matter, you cannot measure it. What you can measure is only the fluctuation in the galaxy distribution. So, you have to assume that the galaxies trace the dark matter, because dark matter is the main matter component of the universe. Now, here there is a possibility that the galaxies may not faithfully trace the dark matter, they may be a biased. So, this introduces the concept of a bias. The galaxies may be a biased tracer of the dark matter. The simplest possibility is a linear bias. What we mean by that is that the galaxy density contrast is related to the dark matter density contrast through a number b, not exactly the same, it is linearly proportional to that. Okay. So, what this means is, the way you interpret it is that if b is greater than 1, the galaxies are more clustered than the dark matter, but they are linearly related. Okay. If b is more than 1, it implies that the galaxies are more clustered, okay, but the linear, it is a linear relation between them. Okay, this is a simplifying assumption which seems to hold at large scales. If you make such an assumption, then what you can do is you can interpret the observed peculiar velocity A, you do this at present. So, A naught is 1, you have H naught f omega which is measured, here you have f omega matter, and then you have 4 pi, here you have x prime minus x by x prime minus x delta galaxy, this is what is observed, x prime t, x prime at present, so time need not be mentioned, d cube x prime, and you have a factor of b, 1 by b, right, because this is delta galaxy by b, the density contrast, galaxy density contrast divided by the bias gives you the dark matter fluctuation. So, what you can measure, this is known, the unknown quantity that you can determine from this is what is called beta, which is f omega matter by the bias. This is the linear density parameter. Linear distortion parameter. Okay, let me put it somewhere else. F omega by beta is called the beta is equal to f omega matter by the bias. This is approximately equal to omega to the power 0.6 by the bias, and this is called the linear distortion parameter. And observations of the peculiar velocity in the form which I have just discussed, and in a variety of other forms, in particularly from what is called the power spectrum, they give you the linear distortion parameter beta, okay, and this has been observationally determined, and it is consistent with omega matter 0.3. Okay, this is one of the evidences that omega matter is 0.3. Okay, but then you have to be able to determine the bias separately. So, I shall not go into the observational issues over here, I shall leave it to you. You can just have a look at the literature, it will give you, you will get a clear picture of the current situation. Let me move on to something else now. Okay. So, let me just summarize. Peculiar velocities are very important, you can measure the effects of peculiar velocities from the galaxy distribution and a variety of other things, and what you can determine from that, one of the very important things you can determine is the value of beta. You can determine this parameter beta. Okay. Now, let me move on to another very important issue. The issue that we are going to discuss now is statistical, is basically the question, how do we interpret the observed large scale structures that we see. How do we interpret the large scale structures that we see? Now, if you want to have a theory to explain the large scale structures in the universe, the theory is obviously not going to predict the fluctuation pattern that we see. A person on another galaxy will see a displaced version of the same fluctuation pattern, right? Whatever theory you have that predicts the large scale structures in the universe is not going to tell us exactly where another galaxy is going to be, right? We see a distribution of galaxies which is not homogeneous. We want to now understand that theoretically. The way we do that is through a statistical. So, we have a statistical interpretation. Okay, so let me explain this. So, what we do is we have this mental picture where the observed large scale fluctuations that we see are the outcome of some process, some statistical process. Okay, that is the basic thing. So, the way we interpret it is that the observed LSS, large scale structures, are the outcome of a statistical process. This is the way we interpret it. Okay, let me explain to you slowly what we mean by this. So, let us first take up what we mean by a statistical process or a random process. Okay. So, let us consider an experiment where we have 3 dice. This is my experiment. Now, when my experiment is that the 3 dice are thrown and you get some result. Now, if these dice are fair, so let us say that there are 3 FAI are fair dice. Okay. So, when I throw them once, I will have say some numbers between 1 to 6 in each of them, and since these are fair, I know that the probability of getting a particular value here is exactly 1/6. Probability of getting a value here is 1/6, getting some value here is 1/6. Okay. So, when I do it, throw it once, maybe I will get 3, 5 and 1. Okay. Maybe if I throw it again, I will get a set of different values. Maybe I will get 6, 2, 2. If I throw it again, maybe I'll get some other set of values. I will get 4, 1 and 5. Okay, so each time I throw it, I cannot predict a priori what value I am going to get. Right? This is a statistical process. What I can predict is the expected value. So, what I can predict, if I call the outcome, if I call this dice, the outcome of this dice x1, of this x2 and this x3, what I can predict is that if I throw this dice many times, I will have a set of all such outcomes, and then if I average over this, I can predict what the mean outcome of x1 should be, for example. So, what I can do is, if I repeat the experiment many times, then I can average and tell you what the expected outcome or the mean outcome of the first dice is. And if it is a fair dice, we know that this will be, how much will it be? It will be, what is the expected outcome of x1? So, it can take values 1, 2, 3, 4, 5, 6 with equal probability. So, it is going to be 3.5, right, that is the mean. 1 plus 2 plus 3 plus 4 plus 5 plus 6, it is going to be 3.5. Okay. So, similarly, I can predict what the what I can predict are the averages. I cannot predict what the outcome of an individual experiment is going to be. I can predict the probabilities, I can predict the averages if I repeat the experiment many times, but I cannot predict what the outcome of a single experiment is going to be. That is the basic premise. Okay. Now, similarly, just try to imagine that the observed universe, the fluctuations in the observed universe is produced by a statistical process. Okay. So, if this statistical process operates once, it will produce one such realization. This is called a realization. So, this is one realization of this statistical process. I have thrown 3 dice once, I will get one realization. 3, 5. So, I have two things. I have what is called a realization, one realization. This is one realization, this is another realization, this is another realization, right. Each time I throw it, I will get one realization, and I have a collection of all possible realizations. So, I do it many times, I will get different realizations. This collection is called an ensemble. So, if I do it many times, if I repeat the same experiment many times, I will get a collection of realizations, and this is what we call an ensemble. And what we can predict are ensemble averages. So, what I can predict is the ensemble average of x1, which we have already, this ensemble average is denoted by brackets like this. So, I have a process, I do many realizations of that process and I then average over it. That is what we mean by an ensemble average, and this will give me 3.5 in this case. Okay. Now, when I am dealing with the universe, the fluctuations in the density which I refer to as large scale structures in the universe. So, we are assuming the model is that there is a statistical process, and one realization of that statistical process produces one set of fluctuation in the universe. Okay. So, our observed universe is one realization of that statistical process. Okay. So, I have a statistical process, let me draw a picture. So, every time it operates, just like throwing my dice, every time I throw the 3 dice, every time I throw these 3 dice, I generate one realization. Similarly, every time this statistical process operates, it will produce, this is my universe, I am just drawing a part of it, my observed universe you may say. It will produce one fluctuation pattern, some fluctuation pattern. So, it will produce a field delta x at some time, say t1, at a fixed time, at some initial time t1. Okay. Now, if this process operates again, it will produce one more realization of this. So, another realization of this will be a different fluctuation pattern. So, here it may look some like this. Okay, this will be a different field delta x. The fluctuation pattern is going to be different. Just like these the values the dice takes is different. Similarly, here the entire fluctuation pattern is going to be different. The fluctuation pattern is produced by a statistical process. Okay. If I do it again, I will get a third realization delta x. Each of them is a different function. Okay. This, okay, some density fluctuation pattern. Now, I cannot predict what the outcome of each of these things is going to be. It is a statistical thing, it is a random process. So, I cannot predict what the outcome of each of these is going to be. What I can predict is the probability of getting some density pattern, some density field, and what else I can predict, the other thing that I can predict is the ensemble average. So, if the same statistical process operates many times, I will produce an ensemble, and then I can average over the ensemble, and this I can predict. Now, we had right in the beginning assumed that the universe is homogeneous and isotropic. The moment you introduce fluctuations like this, the moment you introduce fluctuations, you break the homogeneity and isotropy, right. Now, we will you have broken the homogeneity and isotropy, but now let us consider the statistical process that generates these fluctuations. So, we are going to assume that the statistical process that generates these fluctuations, that itself is homogeneous and isotropic. So, the statistical process that generates the fluctuations is homogeneous and isotropic. So, what we have is statistical homogeneity and isotropy. Okay, so we do not have the background space is not homogeneous and isotropic, but the fluctuations that are there in it are statistically homogeneous and isotropic. The process that generates these fluctuations does not have any preferred origin, neither does it have a preferred direction. That is the basic assumption. So, the way we interpret the cosmological fluctuations, the cosmological structures, is that they are the outcome of one realization of some statistical process, okay. And this statistical process is homogeneous and isotropic. Let us see what this implies. So, let me draw a picture first. We have these realizations. So, we have many realizations of this same statistical process. So, let me just draw them here. Okay, each of them is one realization of the same statistical process, and each of them so is one density fluctuation field, different realizations. Okay. Now, let us ask the question, what is the ensemble average of delta, the density fluctuation, the density contrast at some point x, fixed point x. Let us say at this point x, okay. So, this is my position x, same point. So, what we will do is we will generate many realizations of this statistical process, take the value of x at each point, at the same point in each of these realizations, and then average over all of them. Okay. Now, if this had a non-zero value, the value would then depend on which position I looked at, right, but that would break statistical homogeneity, because then this point would be special, the value would be specific to this point. So, it is clear from this that the mean value, the expectation value, the ensemble average of delta x should be 0. It cannot depend, it cannot have a non-zero value. Okay. So, the expectation value of the density contrast is 0 across the ensemble. Which is also quite obvious, because the delta is the difference from the mean velocity, the mean density, and if I average over all, I should get back the mean density. So, this has to be 0, but to put it in a proper footing, we interpret it in terms of the statistical homogeneity. Okay. So, what else can we now? This does not tell us anything much. Okay. So, the next thing we have to now somehow characterize the density fluctuations. So, the quantity which we can, a quantity of interest that we can look at is what is called the 2-point correlation function. So, what is this? This is as follows. There is one point x1, another point x2. So, there are 2 points now. Okay, let me draw a picture here which is more clearer. Let us simultaneously take 2 points x1 and x2. And we will take the density contrast delta at the point x1 and the density contrast at the point x2, multiply these two and then take the ensemble average. So, now let us see what we can say about this from the considerations of statistics. This is called the 2-point correlation function. Okay. So, we have the density fluctuation at the point x1, we have the density contrast at the point x2, we multiply them and then take the ensemble average. So, we take these 2 points, same 2 points in all the realizations, find the density here, density here, density here, and multiply them and then average over all the realizations. Okay. This is called the 2-point correlation function. It will be a function of xi, it is denoted by the symbol xi, it is a function of x1 and x2, the 2 positions. In general, it is a function of the 2 points. Now, if this is to be statistically homogeneous, then it cannot depend on where I choose the origin. So, statistical homogeneity means, what it implies is that if I take these 2 points, if instead of these 2 points, if I were to shift the origin and consider these 2 points, the 2-point correlation function would be the same. If this were so, irrespective of where I place the origin, then it will be statistically homogeneous, right. Homogeneous. So, homogeneity means it does not have a preferred origin. Wherever I sit, I will see exactly the same thing. So, if I shift the origin from here to here, and if xi does not depend, does not change, so we want this xi to be unchanged even if I shift this. So, this should be the same as xi some constant vector a plus x1 comma a plus x2. And this is possible if xi is a function of x2 minus x1, right. It does not depend on these 2 vectors separately, it depends only on the separation between these 2 vectors. So, if xi is a function of only the separation x2 minus x1 or x1 minus x2, then we can say that it is statistically homogeneous. Okay. So, the 2-point correlation function between these 2 points, if it does not depend on these 2 positions, but it depends only on the separation vector, then we can say that the density fluctuations are statistically homogeneous. Now, next is isotropy. the 2-point correlation function would be isotropic if the 2-point correlation were same for this and let us say for this. If I rotate the whole thing by some angle, if the 2-point correlation function remains unchanged, then it would be said to be isotropic. Okay. So, this will be the density fluctuations, the statistical process would be isotropic if this were independent of the direction. Right. So, if I want, if my statistical process is statistically homogeneous, so if my statistical process is homogeneous and isotropic, it has no preferred direction, it has no preferred origin, then essentially the 2-point correlation function should be a function of only x, where x is the distance between the 2 points x1 and x2. Okay, this is x. If this is true, then my statistical process is homogeneous and isotropic. Okay, so if my fluctuations that I see in the universe are statistically homogeneous and isotropic, the 2-point correlation function of the density fluctuations of the large scale structure should depend only on the separation, not on the direction, neither on where I choose the origin. Okay. Now, the 2-point correlation function, let me just briefly mention it, or okay, let me not go into the observations today. Tomorrow in the next class I shall show you some observed values of the 2-point correlation function. Similarly, you can also define the 3-point correlation function. Let me just briefly mention it. So, here what you do is you take a triangle, three points x1, x2, x3, three different points, and you take the density fluctuation here, here and here, density contrast, and then you have the 3-point correlation function zeta, which is a function of x1, x2. In principle, it is a function of x1, x2 and x3. The ensemble average of delta x1, delta x2 and delta x3. Okay. And if it is homogeneous and isotropic, if the fluctuations are statistically homogeneous and isotropic, then you can express this as a function of only the triangle, the u, if I call this u, v and w, then it does not depend on how I orient the triangle, right. So, it will depend only on the lengths of the sides u, v and w. Okay, it will not depend on the 3 vectors. So, this here it depends on this position 3 number 3, so 3 x y z, this position and this position. So, there are 9 quantities altogether which here it depends on. If it is statistically homogeneous and isotropic, this 3-point correlation function will be the same however I orient the triangle. Wherever I shift the origin, it will still be the same, it will only depend on the triangle. Okay. So, it will now depend only on the lengths of the 3 sides. If I fix the length of the 3 sides, my triangle is unique, it does not change. Okay. So, I have told you that we believe that the large scale structures that we see is statistically homogeneous and isotropic. That is the model we have, and such a statistical process. So, the large scale structures can be quantified using the 2-point correlation function and the 3-point correlation function and so forth. Okay. What is the physical significance of the 2-point correlation function? Let me briefly dwell upon this and then we shall move ahead. It is no use just discussing it and not appreciating its physical significance. Okay. So, let us see what is the physical significance of this quantity. So, let us go back to this picture. We want to appreciate the significance of this 2-point correlation function. Okay. Now, suppose the density fluctuation here and here are totally uncorrelated, they have no relation whatsoever with one another. Okay. Suppose the density fluctuation at this point, so let me simplify the picture. I have these 2 points, and if it is statistically homogeneous and isotropic, then the 2-point correlation, this is the point x1, this is the point x2. If it is statistically homogeneous and isotropic, then xi depends only on the separation x. Okay. Now, how do we define xi? We take the ensemble average of the density contrast at x1, the density contrast at x2, multiply them and do the ensemble average. Okay. Suppose these two are totally uncorrelated, and let us suppose that these are 2 random fluctuations which can take values +1 and -1. Okay. So, they can take values, delta can take values +1 and -1. Now, so when I look at one particular realization, there will be some, this will be either +1 or -1, this also will be +1 or -1. Okay. So, there are 3 possibilities, sometimes it will be +1 -1, sometimes it will be -1 +1, and sometimes it will be the same +1 +1, it will be -1 -1. Now, if these two are processes, if the value of delta here and here are totally uncorrelated, then these 4 will occur with equal probability, right. Sometimes this will be +1, both will be having the same value, sometimes both will have different values with same probability. So, if I take the average, then the product on the average, so this is going to give a product -1 -1 +1 +1. So, if the values are uncorrelated, then when I take the average, it is going to be 0. So, if the 2-point correlation function is 0, it tells us that the density fluctuation here and here are totally uncorrelated, they have no relation whatsoever. Okay. Now, suppose these 2 density fluctuations are correlated. What we mean by that is, I will consider the extreme case in that whenever this has a value +1, this also has the same value. Whenever this has the value -1, this also has the same value. Okay. So, now you see that you always get a plus value. So, when you take the ensemble average, you will end up with a plus value 1 in this case. This is an extreme case. Okay. Similarly, if they were anti-correlated, then what would happen is, if this were +1, this would always be -1. If this were -1, this would always be +1. So, when you take this, it would be -1, anti-correlated. Okay. So, if this is an extreme case, what it tells us is that if xi x is greater than 0, then I am looking at a separation x. If the density fluctuation here is positive, if there is an excess density here, there is a high probability that you will get an excess density here also. Need not be always, but high probability. Okay, if they are uncorrelated, anti-correlated, what it tells us is that if you have a underdense region here, there is a high probability you will have a overdense region at this distance, and vice versa. Okay. So, positive correlation means that if you get one value, if you get an overdense region, there is a high probability that there is an overdense region surrounding it. Okay, and a negative correlation, anti-correlation means that if I have an overdense region, there is a high probability that at that distance there is a underdense region. If they are uncorrelated, then you cannot say it's equally probable. Okay. So, if you have positive correlation, it essentially quantifies the tendency of the matter to cluster. But if the matter is clustered, then you will have overdensities which are all concentrated in some place. Right, let me draw a picture. If I had a random matter distribution, it would be all distributed like this, random. Okay, I hope this is random. And if I calculate the average density, it would be the same everywhere. But if I had a clustered pattern, this is a clustered pattern, then this region has a positive density, this region has a positive density, this region has a positive density, right. So, if I now look at these length scales, I will get a positive correlation. So, if I have an overdensity here, I will also have an overdensity here, right, here and here. So, this quantifies the tendency of the matter to cluster. Okay, so, the 2-point correlation function, if it is positive, it tells us that the matter is clustered. If it is negative, it tells us that the matter is anti-clustered. Okay. An example is if you look at the population distribution on the surface of the earth, then you will find that the distribution of human beings on the earth's surface is highly clustered. If you find one human being somewhere, there is a high probability that there are other human beings around him. And if you find an absence of human beings somewhere, highly probable that there are no other human beings in that region. Okay, because human beings tend to cluster, they tend to live in cities, in villages, where the density is much higher than the average density. Right, so you have overdensity. Now, an example of, say, let us say, of anti-clustering would be the distribution of tigers. Tigers each have their own territory. So, if you find one tiger, it is unlikely that you will find another tiger within some region, which is the territory of that tiger. Right. So, they are anti-clustered to some extent. So, within a certain length scale, you will find anti-clustering. They avoid each other. Okay, whereas humans tend to congregate. So, they have a positive clustering, positive correlation, then you will have a negative correlation for tigers within some length scale. Okay, so, I hope I have been able to convey to you what we mean by this 2-point, so this quantifies the large scale structure, it quantifies the tendency of the galaxies to cluster together. If it is positive, the galaxies are clustered. If not, if negative, they are anti-clustered. 0 means they are randomly distributed. Okay. Now, let me introduce quickly another okay, before doing that, before going on to something else, how does the 2-point correlation function evolve with time? Suppose I have a density fluctuation, I have put in I have some density perturbations in it, then I know that I can quantify the statistical properties using the 2-point correlation function. How does it evolve with time? Now, we know that the 2-point correlation function is the ensemble average of a product of two density contrasts. So, the 2-point correlation function we can write straight away, the function of the separation and time, this is going to be d square t. So, if I have the 2-point correlation function at some initial time, it is a product of two density contrasts. Each of the density contrasts grows proportional to the growing mode. So, this is going to grow proportional to the growing mode square. Okay, and it is going to scale as the ratio of the growing mode square. Okay. Now, the next thing which I will introduce today is that it is convenient to do this whole thing in Fourier space. Okay, so it is convenient to do the whole thing in Fourier space. So, what do we mean by this? What we mean is that you expand the density contrast. I am dropping the time. So, we are doing it at one instant of time. This we expand in a Fourier expansion. So, this we write as d cube k 2 pi cube delta k e to the power I k dot x. Okay. So, this is the familiar Fourier expansion. We have these, we have this field of density fluctuations. This we decompose into a sum of sine and cosine waves e to the power I k dot x. K are the with wave numbers k, and these have to be combined with different amplitudes. So, the amplitude of each wave number is this delta k over here, right, and this k is the comoving wave number. So, as the universe expands, this also expands. We have encountered the comoving wave number earlier, right. So, k is the comoving wave number. So, what we have done is this density fluctuation field we have decomposed into a Fourier in Fourier space, and delta k are the coefficients of the different Fourier modes. Okay. So, this is just another way of expressing the same density contrast. Now, let us ask the question, okay, let us ask the question, how much is this delta k del star k prime so let us ask the question, how much is this ensemble average? Okay. So, what we have done is that we have decomposed the density fluctuation field into Fourier modes. Delta k are the amplitudes of these Fourier modes. Now, let us ask the question, I take the amplitude of two different wave numbers, Fourier modes of two different wave numbers, take the complex conjugate of one of them, multiply them, and then take the ensemble average. So, I can evaluate these two numbers for different realizations, multiply them, and then do an ensemble average. So, the question is, how much is this equal to? Okay. So, we shall, let me stop here now for today, and in tomorrow's class I shall calculate this.